This module is a direct follow-up to the previous. If you remember last time we left off on this slide. Now what are we trying to do here? We're trying to generalize our understanding, generalize our description of a tensor. We want to describe tensors from this point forward in terms of rank, in terms of covariant and contravariant rank. Those two characteristics alone should be enough to tell us whether the tensor is, for example, a primal vector, a dual vector, a linear map, a bilinear form. We know that a primal vector would have a contravariant rank 1. We know that a dual vector will have a covariant rank 1. We know that a linear map will have contravariant rank 1, covariant rank 1, and just to be complete, write the bilinear form, contravariant rank 0 or no contravariant rank, and covariant rank 2. But in addition to that, we also want to know how to build higher rank, more complex tensors. And so that's what we're trying to do here with the 5 cases we defined previously. We have our original base case, which is the bilinear map. Okay, our rank 3 tensor. And what we said was that we're looking at 4 additional cases, which is what happens if we increase the covariant rank, what happens if we increase the contravariant rank, what happens if we decrease the covariant rank, and what happens if we decrease the contravariant rank. And we've already looked at how these changes are reflected in the general input-output mapping. In this section, we're going to look at some more characteristics and keep moving forward. So, quick recap, we know that with regard to these input-output mappings, generally a change in the covariant rank is reflected in the number of inputs that we see, and a change in the contravariant rank is reflected in the complexity, or I could say the rank, of the output. Right here, we increased the contravariant rank by 1, and so we saw the addition of a new contravariant index. Now moving forward, we can look at a summation-based form of these input-output mappings, and we'll see similar relationships. So here's our base case, and then down here we have the case where we increase the covariant rank. 2 changes. Okay, first, as we saw before, right, we are adding an additional input, which we refer to as VC. But in addition to that, you can see that the number of indices associated with our tensor changes with the rank. So we start off with a tensor that is rank 3, meaning it has 2 covariant rank or 2 covariant indices and a single contravariant index. So that is what we have up here. Now when we increase the covariant rank, we not only add the additional input, but we also must add an additional index, because again, these T's are not consistent moving downward. Each tensor is different. So, right, we need to add this additional index right here, and then also add an additional summing operator, because we need to sum over all 3 of these input related indices A and B. So before we move forward though, let's take a look at how we can create this summation based form of our input-output relationship from this expression back here. And I'm going to use the bilinear map, the rank 3 tensor from the previous lecture, as the example. Okay, so we know that we need to create an expression that generates an output primal vector from some tensor times the tensor product of 2 inputs. And we know that this tensor will have a structure that looks like this. Now, don't pay attention to the sizes. They're not necessarily correct. I'm assuming that all the lengths are 2. But what we have is 2 rows, right? They correspond to the contravariant rank. Then we have 2, what I'll call outer level columns, right? Those represent the first covariant rank. And then embedded within that, each sub-element has two subelements. So in order to isolate a single element of this tensor, we need three different indices. So let's look at how this would translate to a summation-based form. So what I'm going to do is I'm going to try to write this out as cleanly as possible. All right, so each element of this expanded tensor should have three indices. Okay, I'll explain what I'm doing in 1 second. So this element is in the first row, and it's in the first outer column, and it's the first element within the sub-element. The one right next to it, and I'm going to have to write smaller, will be that. All right. Then the second row, everything will be the same except the contravariant index will change to 2. The columns stay the same, but the row has changed to 2. Okay, then over here, again, this is the first row, but now for the first covariant rank, it switches from 1 to 2, right? Because now we're in the second group. It's the first element within the sub-element, right? Again, this is the first, this is the second, this is the first, this is the second. Okay, and then we have T2, 2, and then 1. Might just have enough space here. Okay, T2, 1, 2, T2, 2, 2. All right, so this is our tensor. And if you look at the notation at other places in my text or in this PowerPoint, you'll see that I use a certain symbol to group things together. So I erased some stuff here. I can call, or at least in my text, I call both of these elements together. I generally refer to it as T1, 1, and then I put the mathematical symbol for all. So this symbol right here represents both this and this together. Okay, so now let's go back to our multiplication. So we're multiplying this, and I'm going to leave out the symbols because I'm really running low on space. Okay, VA1, VA2. Okay, shoot, just barely not going to have enough space. I just need a little bit more. Okay, let's see if I can squish this together. All right. So we have VA1 and VA2. And then we have VB1 and VB2. Okay, just barely enough space there. Now, the one part of this product that's not shown here is the need to, and it says here, we assume all products are performed with respect to appropriate contracted ranks. So the thing we have to understand is that this primal vector is multiplied using a contracted product, assuming that the first covariant rank of the tensor is contracted. For this one, we multiply assuming that the second covariant rank of the tensor is contracted. So in short, you can imagine VA1 being multiplied by this whole thing right here, whereas VB1 would multiply by that element and VB2 would multiply by that element. So I'm not going to go down this rabbit hole much further than that. But as you can see, the result is, if you're trying to generate a single element of the output, right? If we have V out 1 and V out 2, all right? Let's say we want to generate a single kth element. That is going to be equal to this times the entirety of this grouped column, this times the entirety of this grouped column, this times the individual element, the first individual embedded element, and this times the second. And so what that leaves us with is, okay, A equals 1. I'm just going to say max. Let's assume we know the size. B equals 1 max. I mean, I guess it would be 2 because we know the size. And we end up with TA, TB, K times VA, A times VB, B. Okay, so I hope that helps. I don't know if that's going to be much more helpful than not talking about it at all. If there's interest, and I see it in the comments, perhaps we'll go back and add another section on these various products, including the contracted product as well as the tensor product. But hopefully this at least sheds a little bit of light of how we go from this form to this form over here. And as you can see, what I've written, right, does match that down there. Okay, so now let's return to what we were talking about originally, which is how this expression changes when we increase or decrease rank. Now, we've already seen that changing the covariant rank is going to either add new inputs, or if we look at this one down here, eliminate inputs. Okay, so here, where we're increasing the covariant rank by 1, we have VC, a new input. And here, where we're decreasing the covariant rank by 1, we have VB, right, is now gone. We also have a change in the number of indices required to locate a value within the tensor. So we started off with this, T, A, B, K, right? It was rank 3, and so we needed 3 indices. However, if we add a covariant rank, we're now adding a subscript index. Remember, the subscript indices are covariant, the superscript are contravariant. And so we see that added, and we also have to add a new summation. And that makes sense because we need one summation for each level of the covariant elements. Okay, now we increase the contravariant rank, and that has a much less pronounced change. We're not going to introduce any new inputs. We do have to introduce a new contravariant index. So let me erase this one right here. And now I'm going to introduce a new index up top as a superscript. And then we also need to change or need to add a new superscript to our output, because previously up here our output was simply V out. Down here we have 2 superscript indices, which is equivalent to V out 1 tensor product V out 2. All right, so the main change is when we increase the contravariant rank, or a new index here and a new index here. Then we decrease the covariant rank. We've already talked about what that means. We get rid of VB. And then we decrease and sorry, I think this is a mistake here, the contravariant rank. Sorry about that. So if we decrease the contravariant rank, what we're doing is taking this, what was initially a vector, okay, which had multiple values, and we're collapsing it down to a single element. And so that's why V out, which was originally a vector, gets collapsed to a single scalar value, and everything else pretty much remains the same. Obviously, we're changing the indices for the tensor, which now no longer there's no contravariant index. So a couple things that we can look at to identify an equation is, if we want to identify what the contravariant or covariant rank is, right, when it comes to covariant rank, we can look at the number of inputs, okay, combined via tensor product. We can also obviously look at the number of subscript indices for the tensor, the main mapping tensor, okay, if it has 2 subscript indices, that means it's covariant rank 2. Now, as far as contravariant rank, right, we can look at the number of outputs, okay, that are combined via tensor product. We can also look at the number of superscript indices associated with the tensor. And so again, when we went from here to here and we increased the contravariant rank, we added that new index. And then I guess also for the covariant rank, we could talk about the number of summing operators if we're talking about the summation based form. Okay, so now I think we have a pretty good understanding of how to adapt our tensor to higher order examples. And we could continue this, right? Let's take one of these examples right here. I'm just clearing some space. Okay, let's say that we wanted to take this case here, and we wanted to increase the covariant rank again. How would we do that? Well, first we'd have to include now a 4th input, which I would call VD with a superscript of D. I would have to include a new summing operator, which D equals 1 to whatever the maximum is. And then finally, we would have to include a new subscript index for the tensor, which we would call D in order to match the input. That would not change. And similarly, we could look at what happens if we add an additional contravariant rank here. We would have another index, P. We would have also another superscript index P for the tensor, and that's pretty much it. The number of inputs wouldn't change. So I think that those are enough examples. So we observe that any increase or decrease in covariant rank results in an increase or decrease in the number of input vectors accepted by the tensor. So we have our tensor, okay, and that is multiplied, and again, this is assuming we're employing the proper contracted ranks, times VA vector tensor product VB, and then that could go on for as many as we desire. So increasing the covariant rank would increase the number there, decreasing the covariant rank would decrease the number of inputs. Then we can increase or decrease the contravariant rank, which results in an increase or decrease structural complexity of the output vector, but perhaps it's just better to say it like this. We have V out 1. Let me clear space here. We have V out 1, tensor product, V out 2, tensor product, ... Okay, so if we increase the contravariant rank, that gets longer. If we decrease, that gets shorter. So the number of outputs increases or decreases proportionally with the contravariant rank. So we can see a direct relationship between contravariant rank and the number of input vectors that are accepted as combined via tensor product, and contravariant rank and the structure of the output, which probably, right, we should just say is the number of outputs that are combined via tensor product. Okay, so now we move on to form and structure. I think this is one of the more interesting parts of the lecture. So how does the form and structure of the tensor change with adding, well, let's start off by adding a single covariant rank. So up here, our original tensor has a contravariant rank 1 and a covariant rank 2. Okay, and we see this in the fact, well, first, if we look over here at the size, it has a single superscript, which corresponds to its contravariant rank, and 2 subscripts, which correspond to its covariant rank. All right, we're referring to the sizes of the inputs as NA and NB, and we're referring to the size of the outputs as NOut1, NOut2, etc. Now, because this is contravariant rank 1, there's only one index that's needed to describe the row. And since it's covariant rank 2, there's two indices required to represent its horizontal position. So the first covariant rank tells us whether we're in the first group or the second group or the last group. The last group is group NA. Then the second covariant rank tells us which element we are within here. Okay, and that would range from 1 to NB. Now, and we've covered this structure already. So what happens when we increase the covariant rank by 1? Essentially, and we can take a look at one element. Let's say we have let me use the letters that we used up above. Okay, so this represents a single element from our original tensor. And if we want to add a covariant rank, what we do is we stretch that out horizontally into a number of subelements, or an array containing subelements. So now we have T, A, B, 1, still K, and then ... that takes us all the way to T, A, B, sorry, I have to put this down here, N, C. Okay, where that represents the length along the third covariant rank. So, and that's what we see down here. So the green underlined element becomes a horizontal array. The red becomes a row-oriented array. The purple becomes a row-oriented array. Teal and white. And as you can see, right, the size changes with the addition of a third subscript, which is indicating now that we need to define the length or the size along that new covariant rank. Now, a notation, interesting part of the notation I can point out is that when we expand this, we refer to this new group as TABK. So almost the same as our original, but to indicate that it has multiple elements, I normally include the all-inclusive symbol. Okay, so we know how to go from here to here. Our original rank 3 tensor to one with an increased covariant rank. So now this one has contravariant rank 1, covariant rank 3. Okay, so then what happens when we go from our original tensor and we increase the contravariant rank? So now what we're doing is somewhat the opposite. So we had an element, okay, and we increase the contravariant rank by 1. And what that does, the covariant rank stretched it sideways, the contravariant rank will stretch it up and down. So what we'll have is TABK1, sorry, my writing is, as I write quicker, it gets more messy. And then ... to T, A, B, K, and then N out 2, which is what we call the length along that new contravariant rank. And I'll refer to this whole thing, which was originally represented over here as such, and I can call it T, A, B, K, and then I'll use all, okay? And that tells us that we're looking at a column-oriented array. If you have an all symbol in the superscript, column-oriented array. If you have an all symbol in the subscript, that's row-oriented array. Okay, so we know how to add both a covariant as well as a contravariant rank. One involves stretching sideways, the other involves stretching vertically. And removing ranks is a lot easier. So we can decrease the covariant rank. And essentially what that asks us to do is, when we stretched out sideways, the covariant rank grew horizontally. Now it's going to shrink. So whereas we have here T1, all elements, 1, that is then going to become simply just a single element. All right, no need for this all, because we no longer have multiple elements. And that's, you can see this becomes this becomes this, etc. Now, one thing I want to point out, I'm sorry, for a while I was using NC to represent the size here. That should be N out 1, both here, 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 here. All of these should not be NC, they should be N out 1, because that's the indicated size along the contravariant rank. Okay, thankfully this one's okay down here. Now, what happens when we decrease the contravariant rank? Now we're compressing vertically, and so all the other rows go away, and we're left with essentially just the first row of our original rank 3 tensor. And then now we have a size with 2 subscripts, which makes sense because it's covariant rank 2. So 2 subscripts. Contravariant rank 0, so nothing up here. So what can we take away from this description is that the form and the structure of the tensor is very reactive, very much dependent on the contravariant and the covariant rank. And really just by looking at these elements, right, you should be able to identify what the covariant and contravariant rank is. And the easiest way to do that is simply ask yourself, how many indices do I need to identify an element? Okay, the number of horizontal elements, okay, the number of columns that exist would be analogous to the covariant rank, and the number of rows analogous to the contravariant rank. Now, if you want to get an exact number, you could say that the total number of rows here, okay, if you remove all the barriers and just leave it as a collection of elements, that would be equal to NA times NB. Okay, and the number of rows, again, if you get rid of all these separators and just have as a collection of elements, would be N out 1 times N out 2. But generally, I don't do that. I like to maintain the separators. Otherwise, it makes things like tensor contraction and contracted products quite difficult. So we observe that increasing or decreasing the covariant rank results in an increase or decrease in the number of columns present within the tensor, okay, as well as its similarly structured coordinate matrix. Now, that's one thing I should point out, is pretty much the structure of these tensors is identical to the structure of the coordinate matrix. Not pretty much, it is, as well as it reflects the structure of the individual elements of the basis set. Right. And again, we already said that if we were to get rid of all the separators, okay, then the width of the tensor would be equal to the product of all of its the length of all of the covariant ranks. Now, if we increase or decrease the contravariant rank, it results in an increase or decrease in the number of rows present within the tensor, as well as its similarly structured coordinate matrix. So if we're looking at the number of rows, this would be the product of n out 1, 2, 3, ... Okay. So we see a direct relationship between the covariant rank and the number of columns within the tensor, and the contravariant rank and the number of rows. And we also gained a pretty good understanding of how to increase and decrease our ranks. If we have an increase, and I think I have a table here, that we can kind of make. So if I were to write contravariant rank, covariant rank, okay, increase as well as decrease, right? What we see is that when we increase the contravariant rank, we take a single element, okay, which I'm just going to represent as t, and we stretch it out into and this is contravariant, so we stretch it vertically into multiple elements. If we increase the covariant rank, we take a single element. Okay, remember, this is just a single element. That's what I mean by t. We stretch it sideways, and that turns it into a row-oriented array. And then essentially decreasing just does the opposite of each one of these, right? So decreasing the contravariant rank collapses the column-oriented subelements into a single subelement, and decreasing the covariant rank collapses the row-oriented subelements into a single element. So hopefully the combination of these various descriptions gives you a better understanding of how the form and structure of a tensor changes as its covariant and contravariant rank increases or decreases. Now, I'm going to put in another pause here because I think this video is getting very long, and perhaps the best way to do this actually is to just split it up based on the various characteristics. So this time, in the first video, we introduced this concept of increasing or decreasing contravariant and covariant ranks. We also just barely touched upon how it affected the tensor, the most general input-output mapping. In this video, I think actually we touched upon two things. We looked at the summation-based form as well as how it affects the form and structure of the tensor. As we move forward, we're going to look at how it affects our coordinate matrix as well as the basis. And I think the basis discussion will be interesting because we can look at how we need to add certain primal basis sets or inverted primal basis sets. And then there will also be a pretty lengthy discussion about the transforms, which is an important, probably one of the most important characteristics to understand, because one of the most fundamental attributes of these tensors is how do we perform transform that coincides with the desired change of basis that we see. And then we can talk about the tensor product space at the very end. So I think we're about 1/3, maybe close to 1/2 of the way through our discussion here, talking about how we can use this incremental increase, decrease of contravariant and covariant ranks, starting from our basis of a rank 3 tensor, and use that to build a general, more broad understanding of how to build any tensor of any rank and what the associated characteristics would be.